Hi, and welcome to section 7.4, which is trigonometric substitution. Now, trigonometric substitution, we're actually going to be using that when we have integrals that involve radicals that we can't get rid of any other way. We can't use an integration by parts, we can't use an inverse trig function, we can't use a u substitution. We've got trigonometric substitution. So let's look back at section 5.9 and look back at those inverse trig functions. Now when we look back at these inverse trig functions, these are actually going to help us out with our trig subs coming up. I'd said trigonometric substitutions about as many times as I want to, so trig sub. So we're going to be looking for this general look, so to speak. So arc sine, we're going to think about sine anytime we see a radical that looks like some number square or some number minus a variable squared. We're going to think about tangent if we see something that involves a number plus a variable squared. And we're going to think about arc secant or secant whenever we see the variable squared minus a number. So these inverse trig functions are going to help us figure out what we're going to do with our trigonometric substitutions. So we're going to be looking at problems like this one, and we're going to come back to it and solve it, but I just want you to kind of get an idea of why and where we would use a trigonometric substitution. When I'm looking at this, if it weren't for that x squared, I would be spot on with an arc sine. But I have the x squared, and it's that x squared that stops us from having an inverse trig function. It stops us from having a u substitution, and of course, because it's in the denominator, it stops us from having an integration by parts. So there's not a lot we could do with this until we have trigonometric substitution. So let's kind of see the game plan here, because it sounds really hard. It's hard to say, but let's see what goes on. Now, what we're basically going to be looking for is we're going to be looking for a radical that fits into one of three forms. Number minus a variable squared, number plus a variable squared, and variable squared minus a number. So this one kind of looks like the arc sine, okay, if it were in the denominator. So anytime we see something like that, we're going to make a substitution of x equals a sine of theta. Okay, that a, of course, is going to relate back to this guy right here. Now, what we can do is we'll go through this and we'll solve for our trig function. So if I solve for my trig function, I'm going to have x over a is what sine of theta is equal to. So when I go over here to my triangle, and yep, we're going to make a triangle just like we did in the good old days. Sine is opposite over hypotenuse. So we're going to find this missing side. It's the hypotenuse squared minus your opposite side squared, square rooted. And doesn't that missing side look a little bit familiar? Okay, so by looking at what we have underneath the radical, we're going to think about which inverse trig function this looks like, and we're going to set up a regular trig substitution, not an inverse trig substitution, just a regular. So it looked like arc sine, so we're going to use sine, and we're going to make up our little triangle. Okay, if we have something that looks like this, that kind of looked like tangent. So same thing, we're going to let x equal a times tangent. Once again, if we solve for our trig function, that gives me the tangent is equal to x over a. So if this is my theta, opposite over adjacent, and wouldn't you know, the missing side is a squared plus x squared. Crazy. Okay, so added together, we're going to think tangent. Our last one, if the variable comes first, it's positive, we're going to think secant. If we were to solve this for our trig function, okay, so remember, secant is hypotenuse over adjacent, so this guy right here is our x squared minus a squared. Okay, so we're going to use these trig substitutions to help us solve our equation. So we're going to be doing a big substitution, integration, and then we're going to be doing a big substitution back. So let's look back at our problem number 1. All right, so when I look at this, once again, I know it's not a u substitution because I have an x squared. It's not my plain ordinary inverse trig function because once again I have that x squared. So that x squared is really kind of cramping our style. Well, our variable is the one that's being subtracted, so that screams sine. So I'm going to let x equal a sine of theta. Well, a is the square root of 9, which is 3, so that's going to be 3 sine of theta. Okay, so I can already set up my triangle if I wish to do so. That's going to be theta. This is going to be my x. This is my 3. And this is my square root of 9 minus x squared. Okay, now we're going to be substituting things out, and just like with u substitution, if you substitute out one x, you got to substitute all the x's out. The dx also has to go. So it's not going to be enough for me to just know what x is equal to, because yeah, that would get rid of this x, but I still have a dx. So I need to find out what I'm going to substitute in for my dx. So I'm going to look at what x is, and I'm going to differentiate. So the derivative of 3 sine of theta is 3 cosine of theta d theta. So I'm honest to goodness going to be differentiating so that I can now substitute everybody out. So my dx is 3 cosine of theta d theta. X squared, well, x is 3 sine of theta, so x squared is going to be 9 sine squared of theta. Inside the radical, I'm going to have 9 minus x squared, which is 9 sine squared theta. Okay, and then all I'm going to do at this point is I'm going to start simplifying some things. All right, I know 9 minus 1, I can factor. I'm going to factor and take out my perfect squares. I'm going to try not to skip any steps, but note that you can once you feel comfortable to do so. So what's underneath the radical? I can factor out that 9, and then that's going to give me 1 minus sine squared. Okay, well, what is 1 minus sine squared? Oh my goodness, if you said cosine squared, you're a winner. So I end up with the square root of 9 cosine squared. Now that we only have that one term in the bottom, I can take the square root of that. I'm going to be filling up this whole slide. 9 sine squared theta times 3 cosine theta. All right, so now that I come to this point, what's on top can cancel with some of the stuff on the bottom. So that 3 cosine is going to cancel with that 3 cosine. I'm going to come up here. Boy, I'm kind of running out of room here. All right, don't panic. It's all under control, kids. So I have 1 over 9 sine squared theta. Ooh, I have my d theta up there too. Well, 1 over sine is cosecant. So I have 1/9 cosecant squared theta d theta. And isn't it a wonderful thing that cosecant squared, we can integrate that. Cosecant squared is negative cotangent. So we end up with negative 1/9 cotangent theta plus c. Now, remember how we started off with x's and then we made this trig substitution in here, so we had all these nice thetas and so forth? Well, that's not how we started this party, so we can't end the party there. So kind of like u substitution, if you substituted u's in, you can't leave u's in the problem. Same thing here. We can't leave thetas and trig functions in the problem because that's not where we started. Well, cotangent is adjacent over opposite, so I'm just going to substitute that back in. So you will literally be using your triangle to substitute your way back. So we've got negative square root of 9 minus x squared over 9x. So at this point, when you get to this point, to substitute back out, you actually know that cotangent is opposite over adjacent. Oh, sorry, adjacent over opposite. Yikes, adjacent over opposite. Okay, so that's how we got this guy right here. All right, so this is our final answer. Don't forget your plus C. Goodness gracious, we don't want to do all this work and miss one because of that. Holy moly. Let's try another one. All right, so this one looks a little spooky because I had to handwrite in the integral because somehow it disappeared. Anyway, when I'm looking at this problem, I'm thinking, well, wait a minute. This is supposed to have a radical in here somewhere. This doesn't have a radical, so we're going to rewrite it. I can rewrite this instead of having this quantity to the 3/2 power. I can take the square root of the quantity and then cube it. So now I have that radical showing. That's going to let us know we need to use a trigonometric substitution. Now on this one, as I look at it, I can't use a u substitution because I don't have an x hanging around for the x squared plus 1. I can't use an inverse trig function because there's no inverse trig function that has a square root and a plus sign. So looking underneath that radical, it kind of looks like tangent, so that's what we're going to do. Our x is going to be a times tangent of theta. Well, a is 1 in this case, so that makes that kind of nice. When I set up my little triangle, it's already solved for my trig function, so theta is going to equal opposite over adjacent, so opposite over adjacent, which in this case would be 1. And then my missing side is x squared plus 1 square rooted. So if I'm going to let x equal tangent of theta, then I have to find out what dx is going to equal. Well, the derivative of tangent is secant squared. Theta d theta. All right, so now that we know what x is, we know what dx is. Really, this triangle, we're not going to use this until we have to substitute back for our final answer. So really, all of this stuff right here is what I'm going to be using. All right, so let's get to going. I'm going to push it way over here just in case we need the space, and y'all know how I write. I don't know how that turned out to be so southern, but anyway. X squared would be tangent squared. And don't forget we're cubing that. So we're just going to look for things that we can do. Oh, and somebody let me forget to substitute out the dx. I'm going to go home. Okay, so the dx, don't forget that's secant squared theta d theta. Okay, there's got to be all thetas, all u's. You've got to make sure if you're substituting, substitute it all. We cannot do this half-heartedly. All right, so now we're going. Now we're cooking, kids. Hold on. So we've got the square root of tangent squared plus 1. When you've got a square root, you can't have two terms in there. You've got to do a quantity squared before you can kind of simplify anything in there. But I do notice tangent squared plus 1, that's secant squared. So you're looking to see if there's an identity or algebra that we can use to get that knocked down to one term. Because now the square root of secant squared is secant. I was like waiting for you guys to answer. You can answer when you get back to class. Okay, so square root of that is secant to the 1 power, and then you've got that cubed. Okay. Well, you've got secant squared over secant to the 1 power, so that's just 1 over secant. Well, 1 over secant lost my d theta. 1 over secant is cosine. And the integral of cosine is sine plus c. So I look over here at my trusty little triangle here, sine of theta. Sine is opposite over hypotenuse, so I will make that substitution. I don't have to rationalize or anything along those lines. So yay! All right. Okay, let's look at our last example. Ooh, this one, they're making it super excited because it is a definite integral. Now, if you have the opportunity to use your calculator, then by all means you will use your calculator. But remember, more than half of the AP exam does not let you use the calculator. So let's see what this is going to look like. And it's always good practice anyway. For Pete's sake, we've only had 2 examples. All right, so I'm looking at this guy right here. I notice I have that radical, okay? Well, the radical's in the wrong spot for it to be arcsecant. It's not going to be good for a u substitution because that x is in the denominator. You can't have du in the denominator. So it screams out trig substitution. Because the x squared is positive, that's what makes it secant. So x is going to be a times secant. Well, a squared is 3, so a is going to be the square root of 3. So dx is going to be the derivative of that, which would be square root of 3 secant tangent. Okay. Before I forget, I'm going to go ahead and just draw my little triangle so I can substitute things back here later. Okay, so there's my theta. Okay, so remember that theta is our x. Okay, so that x over the square root of 3, x is the hypotenuse. The adjacent would be our square root of 3. And then this guy is going to be x squared minus 3. All right, so we have that ready for substituting back. Okay, so I'm going to do my little integral here. So I have x squared underneath my radical, so that's going to be 3 secant squared minus 3 all over the square root of 3 secant theta. dx, that's the square root of 3 secant theta tangent theta. So I've got everybody substituted into the theta world. I now need to make sure these limits are in the theta world. Okay, so if I go ahead and change my limits, let me just put that over here to the side, changing the limits, change limits. Okay, so I'm going to put that limit in, so 2 equals the square root of 3 secant theta. So if I go ahead and solve that, I need an angle, and guess what? It's special, that has a secant of 2 over square root of 3, or cosine of square root of 3 over 2. That theta is going to be pi over 6. Okay, so this new guy up here is pi over 6. And then for the next limit, oh my goodness, I'm so going to run out of room. We've got square root of 3 is equal to square root of 3 secant theta. So we're looking at where secant of theta is equal to 1, which is at 0. Okay. So I have these now. I don't have to go back to the x world if I don't want to. So really, I guess I don't need this triangle after all because I'm not going back to the x's. All right, so let's see what we can do here. What color haven't we used? Ugh, this looks like a clown threw up. Okay, so square root of 3 secant, square root of 3 secant, those are going to cancel right away. I'm also going to look inside here and factor. I'm going to try to do some multitasking here because I'm running out of room pretty fast. So if I factor out that 3, I am going to have secant squared theta minus 1. And then this is times tangent. Oh, I lost my d theta. There we go. Okay. Well, like I said, I'm kind of running out of room. So this secant squared minus 1 is actually tangent squared. Okay. So I have square root of 3 tangent squared. So I'm going to take that tangent out. The square root of 3 is going to have to stay. So I have 0 pi over 6. So I have square root of 3 tangent times tangent. So that's going to give me square root of 3 tangent squared. Well, I can't integrate tangent squared, but I know tangent squared is equal to secant squared minus 1. And that I can integrate. Okay, I'm going to pull that square root of 3 out in front. Okay, let's see where I can go here. I so apologize for the mess here. Okay, so I've got the square root of 3 times 0. Okay, so I have square root of 3. I just took that out. Okay, goodness. So I have secant squared theta minus 1 d theta. So when I integrate that, I'm going to have tangent. I'm going to put the pi over 6 in and then the 0 in after I integrate the whole thing. Sorry, I'm too far into this to start over. So the integral of secant squared is tangent. The integral of 1 is theta. There we go. Now we're going to take it on back. Okay. So then you're just going to plug everything in. Remember your first fundamental theorem of calculus. You're going to plug tangent of pi over 6 in, pi over 6, and then you're going to subtract, plugging in the 0, tangent of 0 minus 0. So the tangent of pi over 6 is 1 over the square root of 3. So that's going to end up being, let me just write it out. So 1 over square root of 3 minus pi over 6. So your final answer is going to be 1 minus square root of 3 pi over 6. So you're looking to see, can I do a U substitution? Can I do an inverse trig function? If you've got too much or too little or your radicals in the wrong spot, you're going to think trigonometric substitution.